Hello, everyone. In this lesson, well, actually, this clip is just to go over some, the quiz questions we had gone over in class once again. I graded your quiz, and I just wanted to, explain to you. Okay. First of all, for the first question, find the interval of increasing and decreasing. You don't need to do more because in this question, it's not asking even for local max, local min. So you just need to find the interval. And we also know that we just need to find what is the theorem that's relevant for this question, right? Which is increasing, decreasing test. The increasing, decreasing test is going to be used. So we bring that up, right? So to answer this question, we just need to find the first order derivative. On the first order derivative, we have 6x squared minus 18x plus 12. Right? And we need to know when this derivative is positive or negative. And this is a quadratic function. You can use the other method I did in class. You can also use quadratic property. Okay, this is a quadratic function. Right? This is a quadratic function. And it's a parabola. Okay, so this parabola opens up. This parabola opens up. So you can, of course, on the quiz, you cannot graph it, but you can just sketch it. Okay, you're going to sketch a parabola. Okay, and marking the x-intercepts, right? And the x-intercepts is going to be the critical numbers. The x-intercepts are going to be the critical numbers, right? The critical numbers are by setting the first order derivative equals 0, and of course you can factor this here. Most of you guys did the factoring, which is good, right? So then the x-intercept is right there. The x-intercepts are 1, 0, because if we set the first order derivative equals 0, right? And that will lead to the product equals to 0. And then we get the two critical numbers that are going to be x equals to 1 and 2, right? So the two critical numbers separated the number line into 3 intervals. So 1, 0 is 1 point, right? I'm going to put a circle there. And the other one will be 2, 0. So here we go. So let me adjust. We don't need to have so much view. So let's just make the graph a bit more convenient to see. So this is the graph about first order derivative. So it is a positive here, right? It is a positive. I'm going to use some marking here, right? So this is a positive, this is a positive, and this is a negative, right? So that this interval from -infinity to 1 is increasing because it's a positive derivative, and this one is increasing, and between 1 and 2 is decreasing, right? And we just need to describe it. Some of you use the other method, which is also fine. Okay, when you use the other methods, it's consistent. Okay, it's consistent with our picture here. Okay, so you're gonna have a number line like this, right? So there's a 1 here, and there's the number line continues. So there's a 2 there, right? And here's the number line. And so in this interval from negative infinity to positive infinity, that's going to be positive, right? At 1 is 0, and this is a negative. At 2 is 0, and it's going to be positive, right? So if you come out with this. And then, and here we go. You can say f is increasing in the interval between negative infinity to 1, union, or you can say and, right? And the other interval, which is 2 to positive infinity. 2 to positive infinity. And the next one is that f is decreasing in the interval between 1 and 2. That's it. You're done. Okay, you don't need to go further to explain more. So this is the kind of question that you need to identify what needs to be done. Okay. So now let's look at second question. Second question is about using second derivative test, right? So what is second derivative test? So we're going to look for that second derivative test, and we bring that test to us. Right, that's the second derivative test. Right there. So all we have to do is to find first derivative, because in second derivative test, right, we need to find critical number. We need to have critical numbers. So that's critical number, right? And then we test the second derivative's value at the critical point. Let's first find the first order derivative, which is going to be 6x minus 6x squared, right? And factor that, we got 6x multiply 1 minus x, and set it equal to 0, and set the first order derivative equals 0, and we got x equals to 0 or 1. We have two critical numbers. And then we're going to find second order derivative, which equals to 6 minus 12x. And then we can start testing. Right? Right, obviously, the first order derivative at 0 is 0, right? And the first order derivative at 1 is 0, right? So we just follow second order derivative test. Second order derivative at 0, which is just plugging in 6 minus 12x, right? So 6 minus 12 times 0, that equals to 6, it's a positive. And the next one, we plug in the critical number into that, and that's negative, right? Second first order derivative equals 0, and there's assumptions. The second order derivative is continuous near C. Second order derivative is a polynomial. It's continuous everywhere, so that's not a problem, right? So now we found, after we have get this, now we declare that f has local minimum as 0, right? And we plug in 0 in the original function. We plug in 0 in the original function. And it equals to 1. And on the second case, f has a local maximum because the second order derivative at 1 is negative. So this local max at 1. Okay, and then we just plug in the function x equals to 1. So x equals to 1, x equals to 1. And the final answer is going to be 2. So local max, local min are found. So that's how much work you need to do, okay? So you have to be very clear about what this is asked for and what do I need to do, okay? And thirdly, asking about concavity. You don't need to work on first order derivative. You just go straight to second order derivative. So what do we know about concavity? So you go to your flashcards, you learn about concavity. This is one concavity. This is about concavity theorem. And there's also concave up, concave down. And what else? Inflection point, right? There's definition of inflection point. So I'm taking these two. Okay. And there's inflection point. Inflection point is where there's a change of concavity, right? There's a change of concavity, either changing from concave up to concave down or concave down to concave up. So in this case, right, you don't even need to find second order, you don't need to find critical number. You don't need it. So first order derivative is 4x to the power 3 minus 4x, right? First order derivative, second order derivative. Second order derivative, and that's going to be 12x squared minus 4. Okay. And if you like to factor, you can get about 4 factored out, you get 3x squared minus 1. Apparently, this is a parabola again, right? So you can use parabola one more time, or knowing it is a parabola certainly is helpful. Okay, so you know you can sketch a parabola on your paper and mark the x-intercept. Okay, so I'm going to just sketch it, right? So this is going to be just a quick sketch. Okay, just a quick sketch. And I think I can make it a little bit easier. There, okay? So here we go. X-intercept. So we just need to find x-intercept. So what are the points that intersecting, right? So set second order derivative equal to 0, so we can know the points of change. So we set it equals 0, right? You can factor here. Some of you did factor there. That's fine, right? So you're going to solve 3x squared minus 1 equals 0. And be careful about the following steps, right? So these are pretty typical algebraic solving quadratic equation steps. So you take square root on both sides. Okay, taking square root on both sides. It's optional if you rationalize it. So here I'm going to rationalize it. If you don't, I didn't take points off. Okay, and the next step is the square root of x squared. That is equals to the absolute value of x. So the right-hand side is still stay the same. And solving this absolute value equation, so x equals to plus or minus √3/3, right? So we have two x-intercepts, right? So we have two x-intercepts. One is that, and the other one is √3/3. So we just plot these 2 points in the graph so I will show you, right? So these are the 2 points. Put 2 circle there. So these are the 2 points. And here, this is about second order derivative, right? So this is about second order derivative. So their sign, so on this piece, from negative infinity to negative √3/3, that's a positive. That's a concave up, concave up, concave down. That's negative, okay? If you are to use number line, okay, which is comparable like this. Whoops. It's a negative that, right? So this point, and continue the number line, right? So the other point would be positive √3/3. And that will also tell the concavity. So either way, okay, so this is positive, and that's where the second order derivative equals 0. And between these 2 numbers is negative. Oops. And at the next point is 0 above it. It's a positive. Now we can say, okay, this is second order derivative, right? So second derivative tells the function, the original function is the concavity. So you say this is a concave up, concave up, right? And then in the middle is a concave down, and that's concave up, right? But we do expect you to say F is a concave up in these 2 intervals, okay? One is from negative infinity to negative √3/3. And the other interval, right, positive √3/3 to positive infinity. So this is a concave up, and F is a concave down. Concave down in the interval of this one and that one. Remove that negative sign. So that's the answer about concavity. And this point, right? At this point, at x equals to this number, okay, where we can say concavity changes from positive from up to down at this point, right? And then you just have to find the F value, the output. So F of that, we're going to plug in the original function. The original function is right here. Right here, right? And we plugged in negative √3/3 replaces x, and you evaluate it. We evaluated in class. Okay, does it do it for us? Okay, the simplify. Okay, so 22/9. I'm being lazy here, so you can double check. And we also say concavity changes from down to up. Okay, from down to up at the other number, x equals to √3/3. Okay, so we do the same plug-in one more time at the function. They actually equals the same value because in the original function, we have power 4 and power 2. It doesn't change the value. Okay, they're the same. All right, so inflection point, right? Inflection points. We have two of them. One is this piece, this point. It's in x, and this is the output, right? And the other inflection point is this positive √3/3, comma 22/9. That's it, right? You can see when we are looking for concavity, you don't need to find critical numbers. You just go straight to second order derivative and discuss about the sign of second order derivative. Okay, that's all. Thank you for watching.